that will help to solve optimization problem in really interesting way. That one kind of thing we are calling it augmentation kind of approach will come here. That means we have to uh, take function and constant in together to define a Lagrangian, and that Lagrangian becomes an unconstant problem, and we will try to find optimal value of that Lagrangian. In that perspective, the decision variable or primal variable, it will be converted into in term of Lagrange multiplier, or in short we can name those Lagrange multiplier that duality variable. So that when you try to minimize Lagrangian with respect to a given optimization problem, in that process of minimization of Lagrangian, you come across to see the relation between primal variable, that x, what we used to say, and the dual variable, that Lagrange multiplier. So those kind of relation we will come to see that, and later we will put that primal decision variable in term of dual variable in the Lagrangian, and the resultant would be our dual function, and we need to maximize, and that dual function always happens to be a concave function. So concave function, so at the beginning I might have already told that convex optimization problem are, there are two type of convex optimization problem. One is where we have convex objective function, and if you are having objective function, then we need to minimize that convex objective function over convex set. So this one is one kind of convex optimization problem. That means we are minimizing a convex function over a convex set. So here we can put a condition like this way. Here the function involved is convex, f is convex. Okay, and the constant, or simply you can say that the feasible set C, the constant set C or feasible set C, it is a convex set. So both happens to be convex in nature. Function, the involved function, and also the constant, both are convex in nature. So it is a convex, one kind of convex optimization problem. Okay, and there is one more type of convex optimization problem, is that uh, I'm saying that this one is the first convex optimization problem. Second one is that suppose our objective function happens to be concave kind of function. So if we are having a concave function, then we need to maximize that concave function. So maximizing a concave function over a convex domain or convex feasible set is a what? It is a convex optimization problem. So this is the second representation of convex optimization problems. Here, what is happening when you do maximization of concave function? So here, this f is call it concave function. Here, this f is concave function, and better I would like to change the notation for second case. I would like to take in place of g f, I will take g notation for concave kind of objective function. So g of x, so we are maximizing g of x, where g is a what kind of function? It is a concave function. Okay, did you get? Anyone is having any issue? Several times I used to say that. So g is a concave function here. Why I am calling all these? Because when you will discuss about Lagrange duality, that time the dual problem, it will be always the objective function of dual problem, it would be always a concave function. But when you apply a conjugate duality concept, that one is due to Fenchel. He was a very famous mathematician, I think, from Princeton. So in that case, that conjugate kind of dual function happens to be uh, convex. But if you find a Lagrange dual, that happens to be a concave function. So that's where we do maximization of concave function over the convex feasible set. So here G is concave and C is convex it. Okay, this is the criteria of defining convex function in general. Okay, so what is happening here? So whatever problem generally in machine learning or system identification, what you observe generally problem happens to be in minimization form. So that problem we are calling it primal problem. So we simply denote it by P, or we can write it primal problem. And when we apply a Lagrange duality over that primal problem, then the resultant problem what we are getting, again that one is a optimization problem. But that happens to be the involve objective function happens to be concave. So this problem we are calling it dual problem of the given primal problem. Dual problem we are calling it. So generally we denote this dual problem simply short uh, letter D, or you can write it dual as well. There is no. So first in today's lecture I will talk about motivation of duality. Why we are studying duality? That Lagrange duality, motivation for Lagrange duality. That tangential duality and other kind of things I had already discussed. And dual cone and polar cone, those things we had already discussed in last class. Today I will especially discuss about Lagrange duality. So first I would like to talk about motivation for duality. Then I will go to discuss about Lagrange duality in detail. And at the last step of this lecture, I will take you example. There you will see that if there is a problem and if you apply Lagrange duality, then the dual problem happens to be very simple in nature, and just from the visual perspective you can get solution of that problem. Generally what is happening most of time, if there is no infinity constant, only equality constant is there, then in that case the dual problem is always happens to be an unconstant problem, and you know how easy to solve unconstant problem. For that kind of problem you are having already algorithmic algorithm, that optimization algorithmic technique we are calling it gradient descent kind of technique you can easily apply in such kind of problem. Okay, so coming to first part of this lecture, motivation for duality. So I have taken one example here. So what we do, consider an optimization problem, very simple optimization problem, that x1 is, we are minimizing this quadratic function x1 square plus x2 square plus 2x. And what kind of function this one? Easily you can identify the objective function is what? It is a convex function. Why? Because from second order characterization you come to know, just always whenever you are having problem, always try to check convexity of that problem as well. If it is not convex, then that means your problem is difficult, and your duality concept will help to or overcome that difficulty level. Okay, so always try to define that convexity as well. So what is the Hessian of this one? Hessian would be just it is identity matrix 2 0. First row would be 2 0, second row would be 0 2. So you can see that this matrix is what kind of matrix? It is a positive definite matrix, or it is a diagonal matrix. Simply, easily we can get eigenvalue of this matrix. It is a 2 2. Both eigenvalue happens to be 2 2. So that's why it is very fine that this given quadratic function is a convex function. Now coming to constant. So here we have taken very simple constant. That one is a fine constant. X1 plus x2 equal to 0. So equality constant happens to be a fine in nature. So very fine, it is giving again a convex feasible state. So this given problem is a what? It is a convex optimization problem, and easily you can find solution of this one. So what is the optimal value of this solution? So optimal value of this solution, this problem is what? Minus 1 by 2. And where does optimal value occurs? Optimal value occurs at this optimal point. That means minus 1 by 2 and 1 by 2. So this is optimal point, and this value is optimal value. So generally the optimal value of a given primal problem, we denote it P star. So that is the reserved notation for optimal value of primal problem. Now, theoretically, what we do, we don't want to directly solve this problem. It right now it looks this primary problem is very easy, and we can get a solution of this one easy. But in general, that primary problem happens to be difficult in nature. So what we do, we will try to take few concepts from completeness property of real number. That it says that it is a, you can see that it is a constant problem, And if you remove the constant, what will happen? You will get unconstant problem. That means your the domain of the problem, it has been increased. So due to in increase in domain area, so what will happen? So definitely the corresponding optimization value, it will decrease. It is a very simple consequence of completeness property, or even from real analysis you come to know. So due to that, if you remove the constant, so definitely it will have this unconstant problem. That means we relax this constant, so this unconstant constant problem will have a lower optimal value than this problem, the given problem. So that's where this unconstant problem we denote it by P naught. So we are getting a relation like this. We say that the optimal value of P naught, it provides a lower bound on the optimal value of the given problem P. Okay, so we can write this fact by the following notation. We say that optimal value of P naught, it is always less than equal to optimal value of the given problem P. Okay, this P is the primal problem what I had already mentioned that. And what we this is the primal problem, and whatever another equivalent problem we are getting by doing some kind of adjustment or relaxation, such kind of problem always give optimal value different notation other than P. So we intensely I have taken notation Q naught star. Okay, and here what is the value of Q naught star? Because the unconstant problem is what? It just we need to minimize what? We are minimizing a quadratic function, even it is a convex quadratic function. X1 square plus x2 square plus 2x. So what is the minimum of this was? Where would optimal value will lie? So optimality condition is just directly you will how you will get, find the gradient of this objective function and equate to 0. That is the optimality condition of this problem. And if you solve this gradient, this equation, gradient of fx equal to 0, and if you simplify, then you will get a solution. So one solution, that means you are getting a stationary point. So those a stationary point happens to be a candidate of optimal point. And because the problem is a convex problem, it is having only one, and it is a strict convex function, so it is having only one optimal point. And what was that solution of this gradient fx equal to 0? Solution was this -1 and 0, because it is a quadratic function. If you differentiate, you will get a linear function, and equal to 0, then how many solution you will get? You will get one solution. So you are getting -1 0. So this is the optimal point of the unconstant problem P naught. And what is the optimal value? Optimal value is -1. You got the optimal value as well. So you can easily see that what was P, no, P star? P star was point from negative half. It was negative half. And Q naught star, what is that? It is -1. Definitely -1 is less than, -1 is always less than what? uh, minus half. That means so minus half is always greater than -1. So that relation, this fact is already valid here. We observed that fact, that when we reduce the when we increase the domain of the optimization problem, or simply when we remove the constant, when we remove the constant one by one, if we remove the constant, it means equivalently we say that we are just increasing the domain of the optimization problem. So that is the scenario. So in this case we are getting a lower value of the lower value. It is this optimization problem here is having lower value, and you can say that that provide one of the lower bound of the given original optimization problem. So in order to find other, there might be many lower bounds. So in order to find other lower bounds, we use the following trick. What is that? So we have to do here augmentation. We are taking a real number mu and consider the following equivalent problem. That means we do augmentation of the given optimization problem, this quadratic problem, with the constant. constant. What was the constant function? It was x1 plus x2 equal to 0. So we do augmentation of the objective function with the constant. In order to that, we are having a new function. This function we are calling it, actually I will call later it Lagrangian. So we are having now, we are minimizing Lagrangian subject to this constant. Okay, so it is fine. Now what we do here, we will relax this constant. After relaxing this constant, then what we'll have, we will have a problem of type p mu, that for different mu we will have different of minimum this these unconstant problem. So it is now an unconstant problem. So it is actually Lagrangian. So where always minimizing Lagrangian, it looks like unconstant problem. So what is happening here, the optimal value of this unconstant problem, it would be always less than equal to the optimal value of the primal problem. This result I just from motivation perspective I am talking it, because from the example later I will establish all these result as well. So this kind of, when equality will come, that kind of result we will call it a strong duality. And if there is a gap between optimal value of the equivalent, that unconstant problem, and the original optimization problem, then we say there is that one is not satisfying a strong duality concept. So a duality, weak duality, a strong duality, those concepts will come later. So further, what we will see that the problem, the optimal now, this class of problem, optimal solution of the class of problem p mu, it where it will have optimal point. So it is simply what it is, just it behave like a quadratic function. So again, find the gradient of the above problem p mu and equate to 0, and by solving you will come to know that you are getting a stationary point as a function of the multiplier mu. Okay, so it is in term of mu. So now, and what would be the corresponding optimal value of the optimal problem, p mu? It will be again, it will define in term of the multiplier mu. So it is the optimal value of the this quadratic problem, it will take, it is again a quadratic in mu. That one, you just do simplification here. So after simplification, what you see, you see q of mu, it is just negative of mu square by 2 minus mu minus 1. So that means uh, here it forces that we got a lower bound of the optimal value of the given primal problem as a function of mu. It is a function of mu. You can observe that. So this uh, optimal value of primal problem is bounded below by this kind of, this quadratic function. And what will happens, so if you are willing to solve this problem uh, with respect to mu, what would be solution of this one? So just do solution of this one, find the solution of this one. Solution will something it will come around -1 or something like that. It is what, it is an unconstant problem, because mu is associated with equality constant, and any multiplier which is associated with equality constant always can take any value, negative, positive, whatever else. So there is a region, that region I will discuss later. So if you just do, it is a simple unconstant kind of problem. What you do, find the gradient of this one. What would be gradient of uh, this dual function? So gradient would be uh, twice of mu divided by 2. That means uh, mu plus 1 equal to 0. That means negative mu. Sorry, mu equal to -1. You are getting, you are getting value of mu. Okay. Substitute back this mu equal to -1 here in this objective function. What would be answer? It would be uh, negative half minus 2, and simplify, and then it, what would be this? uh, no, here if you put it mu is equal to -1, so if you put it, it becomes +1. So -1 and +1, it both will cancel out, so you will have just negative half. So you are getting a value of q star is what? value of q star is nothing, just it is negative half, and it is always less than equal to p star. What was the value of p star? In the first problem we had already seen the solution. So p star less than equal to, see here, p star was 1 negative of half. So what we observe here, here q star is equal to p star. So what does it say? It is saying that it satisfies a strong duality. When there is a strong duality concept, then the uh, optimal value of primal problem is equal to optimal value of dual problem. So this is the situation of a strong duality. Otherwise, what is happening? Optimal value of dual problem is always less than less than optimal value of the primary problem. In general, it is happening. If there is a strong duality concept, then equality will come, equality will come. So that is the scenario. So what is that now? You can see here dual problem. So your dual problem is now what? You are minimizing a dual function in the term of multiplier. So this is always giving a lower bound for the primal problem. So it is duality is one way to find lower bound of the given optimization problem. So further, we can see it here. Uh, I had already discussed everything, all these in negative value. So this is the scenario of a strong duality concept. So I'm coming to discuss actual main concept of this lecture, that we are calling it Lagrange duality. In last class, I had already introduced Lagrangian. So just I would like to uh, recall it again, and later I will go to Lagrange duality. So suppose we are having an optimization problem where we minimize an objective function f of naught over subject over these constants. So these are inequality constant, these are equality constant, and optimal value of this problem is p star here, but we don't know p star. What is p star? Also, we don't know x star. Okay, so just for the sake of simplicity, we have written this notation, and now we need to Oh, so we don't know P star, but we can find a lower bound of P star through duality concept. Okay, for that, what we do first, we need to define a Lagrangian. How we do define Lagrangian? It is just talking about augmentation of the given objective function and the all the constants involved in the optimization problem. Okay, or other way also you can say that it is a weighted sum. So you define a weighted Lagrangian is a weighted sum of objective function and the given constant, where we introduce the coefficient or this multiplier with lambda and mu I, we are calling it Lagrange multiplier. Lambda is coming with respect to infinity constant, and mu i's are coming with respect to equality constant. So this is the term of Lagrangian. Now we are coming to discuss about Lagrange duality or Lagrange dual function. So Lagrange dual function G we define as minimum of the Lagrangian over primal decision variable x. Remember that here the Lagrangian is having three different types of variable. First variable x, it is directly coming from the primal variable. So you can call it primal variable. Okay. In short, I am writing it p dot v dot, and lambda. All these are coming from Lagrange multiplier. Mu is also Lagrange multiplier, but later I will call this 12 variable. So right now just put it Lagrange multiplier. Okay. So we are minimizing Lagrangian, remember, only with respect to primal variable. Okay, when we minimize that time, we are not just doing anything with lambda and mu, just we are minimizing with respect to x. Okay, so you can say that simply you are trying to eliminate x in term of lambda and mu. So that's way your Lagrange dual function, it will be always a function of Lagrange multiplier, because due to this infimum operation, it is one kind of elimination of the variable. So x will be eliminated in term of lambda and mu. Okay, So in total you can say that Lagrange uh, dual function, it is what infimum of this augmented sum. Okay, here the dual function g, it is a concave in nature. So you can say that you can ask why it is concave in nature. So if you look in the definition of the Lagrange dual function, what you observe that? So here we minimize with respect to x. So definitely that x will be exhausted. It would be known. It will be not here. So what is remaining thing? It will be here. We observe lambda I, it is in linear in term, and mu I, it is linear in term. Later we will see that x will be converted into lambda. In that way some nonlinear component of lambda and some nonlinear component of mu will also come. But in actual, if you observe that, so it is a linear function of lambda and mu. So that's way linear function is what? It is always giving a concave pattern. It is a convex as well as concave in nature. But when you put it like simplify, so it take a concave, pure concave nature, structure of this Lagrange dual function. Okay. So and also this Lagrange dual function is satisfying lower bound property that this uh, uh, this Lagrange dual function is always bounded above by optimal value of the primal problem for every lambda greater than equal to 0. And what is mu? Mu is unrestricted. Mu can be negative, positive, whatever. So it is mu is unrestricted value. Here it is unrestricted. Restricted. Okay. So that is the scenario of defining Lagrange dual function. If suppose x is feasible, one proof regarding this I have already discussed. Whatever things I discuss here, proof is already highlighted here, and that is this one is analytical proof. Suppose x is feasible and lambda is component wise positive greater than equal to 0, then definitely the objective function will be greater than Lagrangian. Why it would be greater than? Because we are having objective function. Apart from that, this term are coming lambda I happens to be greater than equal to 0. But what we observe, also we are having this constant function fi. And what is the condition of our fi? Fi happens to be less than equal to 0. So that means you are multiplying a positive quantity with this inequality. So again, this inequality would be less than equal to 0. That means this product would be, that means every member of this summation would be either negative or at most it would be 0. So that's way this component is just going to decrease the value of this f naught in this summation. And here fi is what? Fi's are equality constant. That means fi happens to be uh, hi, sorry, hi of x happens to be 0. So it is not creating any trouble. So that's way. So Lagrangian would be always less than equal to objective function, because this is the Lagrangian, and Lagrangian involves this non-positive quantity. Call it non-positive quantity. That means at most it would be 0. Otherwise, this every factor of the sum would be negative. So due to that, Lagrangian would be always less than equal to f of x naught. And what is Lagrange dual function? Lagrange dual function, it is infimum of this one. So this one is Lagrangian and it is infimum, that is least value of this one. So definitely least value of Lagrangian would be less than equal to Lagrangian. This Lagrangian. Okay. And this least value of Lagrangian is actually defining Lagrange dual functions. So that's where Lagrange dual function is bounded above by f naught. And what we observe that, what is p naught? P naught is the least value of this f naught. F naught is the objective function of primal problem. So definitely, and we also observe that dual function every value of lambda mu, dual function is less than equal to uh, f naught of x for every x. So what is happening that and p star is or the optimal or least value of f naught. So p star will be also less than uh, sorry, p star would be also greater than equal to this dual prime, this dual Lagrange dual function. That's why we are getting this relation. So all these, if you again willing to understand or want to get a visualization of this one, visualization is very simple. Just go and recall all these are consequence of completeness property of R. So from there it is coming. So go and recall that math one. In math one, I might have already discussed those completeness property before sequence and series. I generally used to discuss completeness property. So recall those things would be clear. Okay, so we have already defined Lagrange and dual function. So what is happening here? Now I will take two example where we will define a Lagrange dual problem with respect to a given optimization problem. So simplest problem I have taken here as an example, least norm solution of linear system. That means suppose we are having a, uh consistent linear system like this way. Suppose we are solving a 2 by 2 system, or simply your uh, a system in R2 we are taking a 2 by 2 system. That means matrix is coming like this way, uh, 1 1 matrix equation, 2 2, and call it one variable is x1, another variable is x2. So equal to uh, equal to call it 1 2, something like that. Okay, or simply even 2 4 also you can take it, there is no issue. So 1 2 is simply I have taken it here. So what is happening here? So what kind of equation this one? This one is what? This equation is a, this equation is having infinitely many solutions. Easily you can observe the infinitely many solutions. Or this equation simply reduced to what? It reduced a single line in R2. That one is x1 plus x2 equal to 1. If you simplify, then this equation will, uh, this system of equation will reduce to a single line. So this linear system is having how many solutions? It is having a infinitely many solutions, because every point on the line is a solution of the system. So but among those infinitely many solutions, what is the solution which is having the least norm? That means that one is having least distance with respect to origin. So this one is a solution, this one is a solution, this one is a solution, all these are solution. So if you see that this point here, 1 by 2 1 by 2, definitely it is in the line x1 plus x2 equal to 1. This point is having least solution, list norm. You can verify that. It is very easy to verify. Just find the norm. And at this point, 1 by 2, 1 by 2, or it is a solution of this equation 1 by uh, x1 plus x2 equal to 1. Easily you can see that if you put substitute 1 by 2, 1 by 2 here, then that point is satisfying the equation. 1 by 2 plus 1 by 2 equal to 1. That means LHS equal to RHS. So 1 by 2, 1 by 2, it is a solution of this equation. And 1 0 is also a solution of this equation, 0 1 is also solution of this equation. So there are infinitely many solutions. Among that solution, this is having least value. You can find norm of this one. What would be norm of this? Find the norm, basically find the L2 norm. So what is the L2 norm of this? Anyone just calculate faster than me? I'm calling it x star. So what would be L2 norm of this? Samdeep, are you able to listen me? No answer. Anyone is listening or not? 1 by 4. Again try to answer. Again just see it carefully. Just you're finding the L2 distance with respect to origin. 1 by 2. Don't, it is not a KBC game. It is not a KBC game. Just calculate it. You don't have option. You have unique solution here. So it would be what? A square root of 1 by 4 plus 1 by 4 plus is coming. So it would be what? Twice of 4, twice by 2 by 4. That means a square root of, or simply you can say that 1 by root 2. 1 by root. Okay, fine. So that is, and what is the norm of this point? What is the name of this point? This point is your uh, uh, 0 1. What is norm of 0 1? L2 norm of 0 1? I am directly putting norm here. L2 norm. What is L2 norm of 0 1 or 2 norm? It is again you are talking about a square root of 1 plus 0. What is the square root of 1? A square root of 1 is what? 1. So norm of this point 0 1 is 1. Norm of this solution 1 0 is also 1. So which one is having least norm? Definitely this point is having least norm 1 by 2 1 by 2. Value is 1 by root 2. 1 by root 2 is always less than 1. So that's where you are getting a solution of this system which is unique and having list now. So that is the optimization problem. So this problem we will try to solve in. We will first find dual problem of this Lagrange dual of this problem. So we are having a problem that means we are minimizing uh, x transpose x subject to ax equal to b. In such a situation that ax equal to b is having infinitely many solutions. That means it is a consistent system and having infinitely many solutions. Then we need to define Lagrangian of this given optimization problem. So again, how we define Lagrangian? Here we are having equality constant. So first, this objective function is coming plus with respect to equality constant. What Lagrangian multiplier we are taking? We are taking mu. So mu transpose a time ax minus b. We are having this Lagrangian, and now we need to get Lagrange dual function of this problem. So how we will get? So we have to minimize this Lagrangian with respect to x. So in order to minimize this Lagrangian with respect to x, so we need to differentiate. It is a very interesting kind of. It is a very nice and a smooth function. So we need to differentiate L with respect to primal decision variable x to get dual function. So what is the gradient of L with respect to x? So if you simplify, it is a linear function 2x plus a transpose mu equal to 0. And if you simplify, that x is what? It is nothing just negative of 1 by 2 a transpose mu. So you have already seen that no x is in term of mu. Substitute back and you will get your this dual Lagrange dual function. So what is Lagrange dual function? It is quadratic in nature. Quadratic, it is a function in term of mu and quadratic in nature, and it is a very nice function. And here, what is mu? Mu is involved. It is involved with respect to equality constant. So mu is a what? It is a unconstant uh, dual variable. So just this problem has been reduced, this optimization problem has been reduced to this problem there here. We have to maximize this dual function. This is the quadratic dual function, and we don't have any constant over this quadratic function. Mu can take any value. So just you minimize this quadratic function. And what kind of here the coefficient matrix A into A transpose. So it is a very nice matrix, and also it is positive semi definite, easily you can check that. So that's where your this what kind of function it is, this gradual function. Just find the Hessian of this g function g. So has, if you find Hessian of this function g with respect to mu, what would be that? It would be negative of it will become uh, negative half of a into A transpose. A into A transpose is a positive definite matrix. If you multiply with negative, then it becomes a negative definite matrix. So Hessian of this Lagrange dual function is negative semi-definite. That's why the G would be a concave function. It is the definition of concave function. If Hessian happens to be negative semi-definite, then that function would be definitely a concave function. So you come to see that your Lagrange dual function is a concave function, and it will provide a lower bound for optimal value of primal problem. It will just find, so you maximize in such a way, maximum of this one will be definitely less than equal to optimal value of the primal problem. So it is an unconstant problem, easily you can solve this. There is no constant. So you have already seen one dual problem that looks very easy, uh, or easier than primal problem. Another problem I have taken it here, linear program, uh, or linear optimization problem. So we consider a linear optimization problem C transpose X subject to linear constant A, equality constant Ax equal to B, and we put non-negative condition over decision variable. It is actually a standard form of linear optimization problem. If there is any form of linear optimization problem, always we to apply a simplex method, we always convert that into a standard form. So this is the representation of a standard form of linear program. So now we need to define Lagrangian. So Lagrangian, again we will define here what we observe. We are having equality constant, we are having inequality constant. So that's where lambda and mu both will come. So what we do little bit simplification, because in a standard optimization problem, inequality constant always we used to write less than equal to. So when we will get less than equal to, if you multiply with negative, then this coordinate, it is component wise greater than equal to 0, it will be converted. If you multiply with negative, it will be converted into component wise less than equal to 0. Okay, so that criteria, that's way the negative sign is coming. So if you multiply lambda with this included constant, and then we are getting here C transpose X minus lambda transpose X plus mu transpose A minus X. And if you just what you do here, to get your Lagrange dual function, you have to minimize this Lagrangian with respect to X. So segregate all the coefficient of X in together. So these are the coefficient of X, and this is the term which is independent of X. So we need to minimize. So it is what kind of function? It is a linear function in X. So we don't need to find apply calculus technique to find a stationary point of this one. So when this function will be, if suppose this quantity, this coefficient of X is non-zero, so definitely it would be a linear function or affine function, and that affine function having it is unbounded kind of function. So when this linear function will have bounded value, bounded criteria will come when the coefficient of the linear term is 0. So we need to minimize L with respect to this decision variable X to get dual function. So that's why we are putting a condition that this coefficient is 0 in order to get a bounded optimal value of Lagrangian with respect to X. So we put here the coefficient of X C minus lambda plus A transpose mu equal to 0. Then we are getting bounded value of the Lagrangian. This one optimal value is minus B transpose mu. And okay, so this is the dual function. Dual function again we observe that dual function is in term of new. If suppose this one is non-zero, coefficient of X is non-zero, then that time definitely it is going to, if you minimize this one, and it will, where it will go to infinity if you putting non-zero quantity. So that's where it is little bit redundant case. We should not discuss much in detail, we just have to focus on this. So this is the dual function of this problem, Lagrange dual function of this. Okay, and we can easily observe that this function is a linear function in mu. And what is meaning of that? Linear function is both, it is concave and convex. So that's where this Lagrange dual function is a concave function, and it will provide a lower bound for the primal problem. So all these are the story of converting a primal problem into dual problem. In next class, we will discuss further in detail. If you are having any question, you can ask. Otherwise, I'm going to wind up today's lecture. And regarding attendance, go and mark your attendance there in the Google Classroom.